Below to this video will understand the connection between harmonic vector fields and minimal surfaces. Let's recall a parameterized surface S by R of U and V is minimal if its mean curvature is equal to 0, right? And so let's recall the formula where here H is 1/2. Then we'll have an LG minus 2MF plus EN over EG minus F squared, like that. And of course, for these things over here, so 1, of course, is just going to be the first fundamental form, which is going to be E du squared plus 2F du dv plus G dv squared. And 2, second fundamental form, is going to be L du squared plus 2M du dv plus N dv squared. First and second fundamental forms, okay? And so now what I want to do is the following. Let me suppose that our metric has a special, our first fundamental form is a special case. So let's suppose, a proposition, suppose that 1 has a special form, namely it looks like e to the 2f du squared plus dv squared. These metrics over here are sometimes called conformal metrics. These are conformal metrics. Or sometimes in older books they're called isothermal. Okay, and that comes from potential theory. Okay, so isothermal or conformal metrics. Okay. Now, if that's the case, then what happens? Then what does the formula for your scalar curvature reduce to, right? So what will happen over here is that you have a very special first fundamental form. And so what we'll see then is we're going to see that there's no f term, so that's going to vanish. And so in this case, then h is going to be 1/2. And then we'll have an L times G, so it's going to be an L times e to the 2f. There's no f terms, f is gone because it's a conformal metric, plus n times e to the 2f, all divided by e to the 2f times e to the 2f minus 0 squared. And so this is going to simplify just to what? Well, of course, there's going to be an e to the 4f, so the e to the 2f cancels, and so you're going to get a 1/2. And you have an L plus n divided by what? Divided by e to the 2f, e to the 2f over here, right? And so now we have this special formula because the mean curvature turns into e to the negative 2f. And then what are these things? So then L is going to be what? L is going to be RUU plus n is going to be RVV, and these are dot n hat. So I have this representation of what the mean curvature is in terms of the normal vector, in terms of this conformal factor, and in terms of what this is the Laplacian actually of the field, right? So this thing over here is just the Laplacian of R, right? Laplacian of R. Okay, beautiful, right? And therein lies our connection with the term isothermal, right? Because of potential theory. Great. And so now what we want to do is the following. So now, what do we know? We know that RU dot RU is equal to RV dot RV because it's conformal, they have the same coefficients, right? So if I differentiate this with respect to U, what will I conclude? If I differentiate this with respect to U, I'm going to conclude that RUU dot RU is equal to RUV dot RV like this. And then, of course, what I can do is I can pass this v over here to that derivative because the derivative is a self-adjoint operator, right? A negative self-adjoint operator. So I can write this as negative RU dot RVV like so, okay? That stems from the fact that the derivative is anti-symmetric, right? When you do a dot product, okay? Great. And so now I can take this equation over here and write it in the following way. I can write this as RUU plus RVV dot RU, if I throw the RVV over here on the other side of this equation, will I be able to conclude this will be equal to 0? Beautiful. And then similarly what? Similarly, we can see that I can do a v derivative of this. RUU dot RU equals RVV RV dot RV. Like that. Take a v derivative and conclude that RUV RU is equal to what? Is equal to RVV dot RV. Put a v derivative on the other side of the equation, put this u over there, right? And this is going to be equal to, if I do that, I'm going to have a negative RV dot RUU. And so from this equation over here, we can conclude what? We can conclude that RUU plus RVV dot RV is also equal to 0. Now let's think about what these equations tell me together. So together, these two equations over here, these tell me that RUU plus RVV is parallel to n hat, because it's perpendicular to the tangent space, right? And now how do you find out what that is? Well, I know what the coefficient's going to be, so I know that if I look at RUU RVV dot n hat, that's going to be twice h times e to the 2f, right? And so in fact, this allows me to conclude that RUU plus RVV for these isothermal conformal metrics is equal to 2 the scalar curvature times e to the 2f, right? E to the 2f, like so. Beautiful, right? And so now I can summarize this as a proposition. So what's my proposition? So my proposition allows me to conclude what? Proposition for conformal metrics, surfaces with conformal metrics, the surface is minimal if and only if the Laplacian of the parameterization is equal to 0. In other words, what this means that you have a harmonic parameterization. You have a harmonic, these are called harmonic parameterizations. Beautiful. So what we've done now is we've at least for surfaces with conformal metrics, right? We've been able to relate minimal surface theory to harmonic function theory, right? So in other words, there's lots of examples of these. There's lots of examples of conformal metrics. So for example, you can think of like a conoid where you're rotating a hyperbolic cosine, right? That's going to be a minimal surface because it has a conformal metric, right? You can think of also a helicoid, right? When you're basically rotating a helix, that's also going to be a minimal surface because it's also satisfies this harmonic condition. So we'll be able to get a lot of mileage out of this result by saying that if you have a harmonic parameterization of your surface that is conformal to Euclidean space, then you automatically have a minimal surface because the e to the 2f and the 2 are non-negative all the time, so the only way that can be 0 is if the mean curvature is equal to 0, which is equivalent to it being a minimal surface. Thank you very much.